Welcome to a Code Report LeetCode solution video. In this video, we're going to be looking at the solution to problem 1, kth symbol in grammar from LeetCode Contest 70. So the problem states, on the first row, we write a 0. Now in every subsequent row, we look at the previous row and replace each occurrence of a 0 with 0, 1, and each occurrence of 1 with 1, 0. Given the row n and an index k, return the kth indexed symbol in row n. And note that the values of k are one index, so at some point we'll have to do a post-decrement or pre-decrement. So taking a look at the examples that the problem provide, the examples are at the bottom, giving you the n and k, and it also provides an explanation by showing you what the first 4 rows would look like. So in row 1, we start with a 0, and then for row 2, we replace the 0 in row 1 with 0, 1. Then for row 3, we replace the first 0 with 0, 1, and then the 1 with a 1, 0, ending up with 0, 1, 1, 0. And we just perform this algorithm repetitively until we get to the row that we desire. So if we highlight the characters in our rows that match up with our examples, you can see why we are returning either 0 or 1. And the insight that you can use to solve this problem is to note that for each row, for row n, it is essentially row n minus 1 plus row n minus 1 inverted. So for row 2, all we have to do is look at row 1, which is a 0, and take that and add to it the inverted value. So you take 0 and add to it the inversion of 0, which is 1. So you end up with 0, 1. And for row 3, you look at row 2, which is 0, 1, and you add to that the inversion of 0, 1, which is 1, 0. And so using this information, we can basically look at k, and if k is in the second half of our row, we can then shift it to be in the first half and keep track of the number of times we have to do that shift. And at the end of our algorithm, if the number of shifts we did is even, we can just return whether we have a 0 or 1. And if we have an odd number of shifts, then we need to return the inverse. And the way you can think about that is, so here for our fourth example, we are looking at row 4, and k is equal to 5. And so here, because the kth index is in the second half of our row, we are going to shift that backwards to 1. So just subtract the length of the row divided by 2, and then your flips are going to be equal to 1 at that point. And so for the remainder of our algorithm, k is always going to be in the first half of our row, and it'll get down to 0. And because we've only had one flip at that point in time, we're going to return the inverse of the number that we have at that point in time. So let's take a look at the code. We initialize a long s to be equal to 2 to the power of n minus 1, and that's going to be the length of our row. And we initialize a variable flips equal to 0. And so we have a while loop. While the length of s is greater than 2, if k is in the second half, so if k is greater than s over 2, we shift it, and then we do a post increment to our variable flips. And whether it's k is in your second half or first half, we're always going to divide s by 2, so have the value of s. Once we've completed this, our value of k is either going to be 1 or 2, so we have to do a post decrement in order to change that to 0 or 1. And then the last thing to do is, if flips is odd, then we have to change k from either 0 to 1 or 1 to 0, and then just return k. So that's the first solution on how to solve this problem, and that's what I did during the contest. But I reviewed some other people's code, and they had a very, very cute one-line solution. So let's take a look at what motivates that. Oh, and just to note, this is a linear algorithm. Although we're exponentiating 2 to the power of n, we're doing a divide by 2, so basically reversing the exponentiation we did. So it'll be linear in the size of n. So for the second way to solve this problem, we need to notice a pattern, and that's if we take k and then look at k minus 1 and then convert this to binary and then count the number of ones that are in the binary number. So basically count the number of bits that are set. A bit that is set is a bit that is 1. And then we look at basically whether it's an even or odd number of bits set. And if we do this, you can note that this basically has the same pattern as our rows. 0, 1, 1, 0, 1, 0, 0, 1. It'll continue to match our rows in any length. And so using this information, I also found another diagram online that showed the same information a little bit nicer, so that number of bits set in a binary number results in this sequence. We can use the following code. So a bit set is a data structure provided in C++ that you need to pass a template parameter to, which is basically the size of your binary number that you want. And so if you give it k minus 1 and you call the function count, count will return the number of bits set in your bit set. So basically the number of ones in your bit set or your binary number. And if we just return that modulus 2, you'll end up with a solution. So if you are able to recognize that pattern, or you just know it from before, you were able to use this solution. Thanks for watching.